Velocity, aka speed. In this video, we're going to look at two types of velocity and how they are related. First, we got linear velocity. Linear velocity is a measurement of how fast an object moves in a straight path. Example of units would be miles per hour. All right, now in that definition, it describes it as being a straight path. I don't want you to get too stuck on that idea there. Suppose we imagine a car that's driving, right? And car's driving miles per hour. If you have a car that is driving down a windy road, that is okay. It is not technically a straight path, but what we're doing with linear velocity is we're measuring a distance per unit of time, okay? And miles would be a distance, okay? So you're still measuring distance per unit of time. Angular velocity is going to measure something different, okay? Angular velocity is the measurement of how fast an object moves around a fixed point. Example units would be radians per minute. Okay, so for angular velocity, this isn't a distance per unit of time, but what it is actually going to be is an amount of rotation per unit of time. So this is going to refer to an object that is spinning in a circle, object that is moving in a circle, and we're looking at the amount of rotation that has occurred per unit of time, whether that be minutes or seconds or hours, depending on what the object is that we are imagining here. Now, in a circular movement, you can still have linear velocity. You can still talk about how much distance it's traveled, which might be the circumference of a path that it creates. Okay, but the angular velocity is going to be the amount of rotation that occurs. We're usually going to do this in radians. If you do come across a problem that introduces the rotation as degrees or revolutions, the key to being able to do the problems is to make sure that you convert that unit, whether degrees or revolutions, convert that unit to radians. All right, let's go ahead and take a look at the diagram that I have here. The diagram is going to show us both types of velocity, and in fact, we'll eventually use that diagram to build a connection between these two different types. Off to the side here in a couple different spots, you're going to see these little arrows, and next to that would be a V. That V is going to refer to the linear velocity. You're going to notice that it has a straight line there, so that's why it goes with linear velocity. Inside the figure, you're going to have this curved arrow, and that is going to represent the angular velocity, okay, that rotational velocity that we have here. Next to that, this is the lowercase Greek letter omega. That will be the variable that we use to represent angular velocity. All right, let's go ahead and talk about the angular velocity first. What we want to do here is imagine that we have a point that would be on the outside of the circle. Let's just say that it's located here. And this is our fixed point that we are moving around, okay? And that point, we're going to go ahead and say that it rotates that direction because the other arrows are pointing that way. All right, that point may rotate from here all the way to this spot. It might move along the outside of the curve. It would follow this arc length right here, that curvature, all the way out to that spot. And you can measure that change using a degree measurement or a radian measurement or even like a partial revolution. Okay, you can describe that it has rotated theta amount of degrees or theta amount of radians. Most of the problems that we're going to do are in radians, but if you're given something in terms of degrees, you'll want to make sure that you do convert that into radians. All right, so omega is just how much rotation, how many radians have we moved in a unit of time, whether that be maybe seconds or minutes or even hours. All right, the linear velocity is similar to the angular velocity. What we're going to do is imagine that point is moving along the curve here. But instead of talking about the amount of rotation that has actually passed here, we're going to be looking at the distance that has traveled along the edge of that circle. Okay, we're going to be looking at the arc length that has passed. Units for that, it sort of just depends on what type of a problem you have. If the rotation is really big, that might actually be in miles, but you may see it in centimeters or inches or some other smaller type of unit. And for velocity, what you're going to be looking at is that distance that has been traveled. Let's just go ahead and suppose it was in centimeters, so maybe about 2 centimeters. May have rotated 2 centimeters in a matter of seconds, something like that. Next, what we're going to do is look at how the two of these things are related to each other. In the picture, I was able to use the same 2 points here to talk about how we could measure the angular velocity, how it's rotating around, and also talk about the linear velocity. So it would stand to reason that there has to be some connection between these two. If I can put them in the same picture, I can use the same diagram to describe them, and even make those calculations for the linear velocity and angular velocity. There should be some way that we can connect these two together. Okay, all of that's going to start with more or less the definitions of these two things here. Velocity is going to be the measurement of distance per unit of time. Okay, so it's measuring along the length there. That would be the distance per unit of time. Omega, the angular velocity, is going to be the measurement of the rotation or the angle divided by the unit of time. Okay, how far is it rotated that direction? How much space is here per unit of time? All right, so what we're going to do is start with omega. We're going to start with omega, which is the measurement of the angle divided by the unit of time, okay? And then we're going to think back to something really interesting about radian measurements for angles. That theta, that angle measurement in terms of radians, is actually defined as the arc length divided by the length of the radius. That's how we get radians. So if we go to this equation that we have here, omega is equal to theta divided by time, we can actually substitute in for theta s divided by r, which is going to look like this. Okay, now it was a fraction that we're substituting in, so the numerator of that fraction, the s or the arc length, is going to be on the top. The radius, which is part of the denominator, will just end up in the denominator next to the t that we have here. Okay, so now we can describe omega, angular velocity, as the arc length divided by the product of the radius and the amount of time. But when you build this fraction, when you see that one, you're going to notice that you now have an s over t, which is kind of interesting because with theta, we substituted in s over r, but now you can look at s over t and notice that that is the same thing as the linear velocity. That's v. So that part, that is going to get substituted out with v. V is going to end up being on the top of the fraction over the radius that we had introduced a little bit earlier there. And with just a quick bit of cleanup here, what we can do is multiply the radius to the other side, and then of course I got this flip backwards here, but I get the linear velocity is equal to the product of the radius and the angular velocity. Okay, so that right there, this as well, but this is going to be the easier form to work with. This is what's going to bridge us between linear velocity and angular velocity. If you have the angular velocity, you can multiply by the radius. That gives you the linear velocity. If you have the linear velocity, you can divide it by the radius. That's more what you see here. You can divide it by the radius, and that will give you the angular velocity. All right, let's go ahead and see if we can do a problem that relates linear velocity to angular velocity. It says here, the belt on an automobile air conditioner connects metal wheels with radii 4 centimeters and 7 centimeters. All right, so what we have here are these little wheels, and there's a belt that is going to be connected that goes around it, and I'll add that in just a moment here. But you have these two different wheels here, and obviously one is smaller than the other one. The first is going to have a radius of 4 units. Let me go ahead and add that in there. That'll be 4 centimeters. The bigger one is going to have a radius of 7 centimeters. All right, and then for the sake of not having things too confusing here, since both of these are radius measurements, what we'll do is use little r for the smaller one and then capital R for the bigger one, and that's all that means, is just to distinguish between the other one. All right, it says here that the angular speed of the larger wheel is 120 RPM. What that stands for is revolutions per minute. All right, you're going to notice here that a question hasn't actually been posed. Overall, the question that we're going to be answering will be C, but what I'm going to do is take you through these steps just to get to that answer there. Okay, so C is going to ask, what is the angular velocity of the smaller wheel in radians per second? All right, so what ends up happening is this has a rotational speed, 120 revolutions per minute. It has that rotational speed. It's going to be connected to the other one with a belt. You can also think of this as maybe like a bicycle with a chain. Okay, so it's connected together. And what I want you to notice from the beginning here is that when the big one rotates here, it's going to move the chain, or in this case it's the belt, I'm thinking of the bike now, it's going to move the belt that amount of distance, whatever the circumference is here. Okay, so as that makes one rotation, the belt is going to move that amount of circumference. But that same belt, as it's moving, when it goes to the smaller wheel over here, that wheel is actually going to rotate probably 2 times or so. Just going to estimate there. It's going to rotate more than 1 time, because as that goes through just once and the belt is moving along, and you're going to notice, I hope you'll notice there, that this is going to spin around more. So these are not going to have the same angular velocity. The angular velocity of the little one is actually going to be more than the bigger one, because one rotation, the bigger one, is going to create multiple rotations of the smaller one. All right, so that's what we're going to be trying to figure out, is what is the angular velocity that we have for the little guy here. All right, these questions leading up to C are going to help us organize and get there step by step. Part A, what is the angular velocity of the larger wheel in radians per second? What is it in radians per second? So a little bit earlier I'd mentioned that the key to relating these two things here is going to be radians. Okay, and that goes right back to this whole thing here. You can't substitute in the S over R for theta. You can't substitute that in unless we're thinking in terms of radians. So as our first step, what we're going to do is take whatever the angular velocity was that we've got and go ahead and convert that into radians per second. You can use a technique called dimensional analysis to do this. Okay, what you do is you take your given 120 and you're going to set that up as a fraction, but we're also going to include the units when we do this. So this would be 120 revolutions. I'm going to put REV because later I got to say radians, RAD. Okay, we don't want to get all the R's confused. All right, and that would be per 1 minute, 120 revolutions per 1 minute. That's how we interpret that. Now, what we're going to do is multiply by a fraction that's equivalent to 1. We call these a conversion factor. You're going to multiply it by a fraction equivalent to 1. That's going to change the units from revolutions to radians. Oh, we're also going to have to change, sort of missed that part there. We're also going to be changing it to seconds. So that'll happen separately in the same problem, but in a separate area for that part. All right, so to convert revolutions into radians, within 1 revolution, you have 2 pi radians. You have 2 pi radians. So what we're going to do is put on the bottom here 1 revolution. The top, we're going to do 2 pi radians. Okay, and if we were to multiply these fractions, first off, this is equivalent to 1 whole, because the numerator is the same thing as the denominator, just different types of units are being used here. Okay, so we're going to multiply by 1 whole. That is not going to change the value of the number we have here, but it is going to change its appearance because it's going to put it in radians. The revolutions being on top and then on the bottom, those will cancel. Okay, so it was important that I put the revolutions on the bottom. That way these cancel and it leaves me with radians. Okay, so at this point, if I were just to multiply these together, I would get 240 pi radians per minute. But we got to get to seconds. So what we're going to do is add on another fraction that is going to cancel out the minutes. Okay, 1 minute is the same thing as 60 seconds. Okay, so minutes will cancel, and then what we'll be left with, if you look at your units on the top, you have radians. Units on the bottom, you're going to have seconds, so you'll get radians per second. We just actually got to multiply across here. Lots of different ways you could do this. What I sort of pick up on right away is that 120 is divisible by 60. Okay, so if you divide those two, you're going to get 2, which means then you can do 2 times 2 pi, which is going to be 4 pi radians. All right, and then your unit of time is seconds. Okay, you can also go ahead and multiply across the top, which would give you 240 pi, then 240 divided by 6 is also 4. So you get 4 pi radians per second. And of course, go ahead and leave this in terms of pi here. It does have a decimal form. This is actually going to be 4 times 3.14, so a little bit bigger than 12, but go ahead and leave it in that form. All right, so for part B, what we're going to do is figure out the linear speed of the belt. Like physically in the diagram, the belt is what's connecting these two wheels here. Okay, so we got an angular velocity here. If we can figure out what the linear velocity is of that circle, we can actually get the linear velocity of the belt, which will then transfer into the other wheel, and from there you can then figure out the angular velocity. All right, so how do we get the linear? That is going to come back to the equation we figured out a little bit earlier, which is that linear velocity v is equal to the radius times omega. Okay, and omega needs to be the angular velocity in radians per second. Well, in this case, we want to use radians, it's the main thing. But it is going to be radians per second, which is this right here. Okay, so the linear velocity is going to be equal to the radius of that circle, where all this is originating from here, so that's a 7. Okay, it's going to be equal to 7 centimeters multiplied by 4 pi radians per second. Okay, at this point, I'm going to go ahead and just drop out the units because that part might get a little bit confusing. Just focus on the math here. V is equal to 28 pi. Okay, now the units for that would be centimeters per second. That's what that would be. I just took out the units here because it gets a little bit messy trying to figure out how to deal with all of them. Okay, but linear velocity is a distance per unit of time. The distance that will be traveled is 28 pi. 28 times 3.14 centimeters per second. And be that. All right, and now that's the belt that's moving all the way around. Okay, so everywhere you look on the belt, it appears to be moving at 28 pi centimeters per second. All right, so we're gonna move that over into the other wheel and go back to using the same conversion now. Okay, the radius multiplied by, well, linear velocity is going to be equal to the radius multiplied by the angular velocity. For this question, we are trying to figure out the angular velocity of the smaller wheel in radians per second. Okay, and what we know is that the linear velocity around the edge of that circle is 28 pi. It's 28 pi. Okay, so we'll set that equal to the radius of the little one, which is 4 centimeters. All right, and then multiply that by omega. That would be our unknown there, omega. So if we divide 28 pi by 4, we're going to get 7 pi radians per second. And that is it. Upon reflection, I realize my answer is completely wrong. Nah, just kidding. The angular velocity of the smaller wheel is 7 pi radians per second. Okay, but what I was sort of thinking about here is that at the very beginning of the problem, it gives us the angular velocity of the larger wheel in rotations per minute or revolutions per minute. Okay, so what I think would be a good idea is to go ahead and take that answer that I have at the very end and switch that into revolutions per minute. Make it match what we see here. And to do that, we're just going to use some dimensional analysis. We're going to take 7 pi radians per 1 second, and we're going to convert both the angle units and the time units. All right, so for the radians, 2 pi radians, I'll put that on the bottom so the radians cancel. 2 pi radians is equal to 1 revolution. Okay, so that'll get us into revolutions. And then for seconds, we're going to put seconds on the top to cancel out seconds that we have down here. So that'll be 60 seconds to 1 minute. All right, so that'll leave you the revolutions per minute. All right, math-wise, the pi symbols, those will cancel out. All right, and then if you want, you could divide the 2 into the 60. That would give you 30, and then 30 times 7 will give you 210. So you get 210 revolutions per minute. Okay, so that would also be a good answer, and it fits how the prompt would have been at the beginning. Now, remember that number 210, right? If we compare the 210 to the 120, that should make sense because the big wheel is gonna rotate 120 times per minute. But when it rotates and that belt moves around it, every time that belt covers the circumference of that circle, it's gonna cause this to rotate more than once. I think previously I described it as maybe like twice. Okay, so if I were to double the 120, that would get me to 240. It ends up that our answer is 210.
Wait, there was.